Okay, good. So we can begin. So today, basically, I will go through the steps of trying to describe how the ANN and CNN kind of basically works, and then go on to some basic stuff that we do in CNN, very basic stuff. So that's a part of the tutorial. And so basically, what we will be doing is we have a data, and we have set of data, and we are trying to train a network of some kind on this. So we also need to understand what kind of data we have. Like some of the earlier examples Swagata gave in her lectures, she talked about house prices. So like house price is a final prediction, but things like how many number of bedrooms, where is the location from nearest station or something like that, and other these things, these were called features. Okay, so I have a feature vector or the feature set, so to say, a set of feature that describes one particular. Yeah, sorry.
Your slide is not changing.
No, I'm not. I'm just I'm on the very first slide itself. Okay. So I'm just describing the meaning of the words that is used over here. Okay. So for example, I'm using the word like spatial sequences here. Okay. So what is the spatial sequences would mean? That's what I want to emphasize. So in the example, that very first example Swagata gave, there was no meaning of spatial sequences. It's just a set of data points. Okay. So set of data points were number of bedrooms, size of the rooms perhaps, how many floors it has, square foot area. These things are features. Distance from the nearest market or the transportation or the nearest school, hospitals. These are the various features that describes the worth of a house. And eventually you combine all these features into one single number that comes out to be the price of that property. So those are the features. Okay, so and each house has some values for these features. Okay, so if I have 10,000 houses or even 100 houses, I can just figure out what these numbers are, and from there, if I have a good model, good network, I can predict using one, we will have some kind of ANN to predict the price. Okay. So now what the spatial sequences means is like the images. So it has a meaning. Like the one-dimensional sequences would mean that there is a left to right meaning to it, that I'm moving right on the sequence or moving left on the sequence. Images that we have on our phone, it's 2D sequence. There is a sense of left, right, and there is a sense of up, down. Then there will be 3D sequences. Okay, so left, right would be there, up, down will be there, forward, backward will be there on top of that. Okay, so convolutional neural network is a kind of neural network that we use for spatial sequences, like images. Okay, so let's look at, so let me just remove that. So let's look at here. So very first example of, say, ANN. So we here have, for example, these guys, the first layer is the number of features. So N0 is the number of features that I have. Okay. So same as like how in the case of a house, I could have taken different things as different quantities are computed. Those are features. This is my feature vector. Then in a neural network, I have the first hidden layer, which has n1 number of nodes or neurons. Okay. So once I have this, then what happens that each neuron is like a decision boundary in the space of features. So there are N0 features. That means I have N0 dimensional, Cartesian space, and there is a there's a hyperplane. Now hyperplane usually. So let's take an example for 2D here. So I have 2D examples, and here the hyperplane will be one-dimensional line. So it divides the plane into two parts. Okay. Here there are two lines in this particular image. So it divides into, each line divides the total space into two parts. Okay. So what I mean that on the line, you have a linear combination equal to 0. On one side, the linear combination is positive. On the other side, linear combination is negative. So by computing that linear combination of features, I know which side of this decision boundary I am. Okay. So coming back, so I have this thing that each of this neuron in the first layer, pardon me, each of the neuron in the first layer, it divides the feature space into 2 zones. Okay. Now what happens whenever the N1, that's number of these nodes, is less than the number of features, then what happens that every new node subdivides every zone available. So when I put the first neuron, it divides the full space into 2 pieces. The second neuron, what it does, it divides each of those 2 pieces into 2 pieces further. Example you can give. In 2-dimensional, the one line divides it into 2 pieces. Now when I add the second line, okay, this is the second line, it divides the first part into 2 pieces, second part into 2 pieces. Okay. But if I add a third line, that doesn't happen. So if the subdivisions kept on happening, then what will happen? The number of zones I can divide my feature space into will be 2 to the power n1, where n1 is the number of neurons in the first hidden layer. But that doesn't scale like this. Here, note the n1 is in the exponent. So number of zones increases exponentially. Okay. But when n1 is much, much larger than n0, which means the number of decision boundary is much, much larger than the spatial dimensions of the features, then the n1 is no longer in the exponent, n1 sits in the base. And n0, which is a constant, the number of features is constant, that becomes exponent. So from the exponential behavior to polynomial behavior, of course, polynomial to a very high degree, it changes the number of zones kind of goes into polynomial. So example of that, we can see here that the first line, okay, in 2D divides into 2 pieces. Now, no matter where I put the second line, okay, it will cross with the first line if they are not parallel. Then and usually the second line should not be parallel. So then it divides into 4 pieces. The moment I add the third line, that means my n1 is larger than n0 now. n0 is 2, and my number of n0 is 2, that's the number of features. Now my n1 is 3, so ideally I should have had 2 to the power 3, but I only have 7 zones here in this particular case. So it is started to deplete number of zones. Next, when I add the fourth line, okay, this red line I added over here. So when I added that, what it did, it only whatever number of zones that were there, it added only 4 to that. So if you just see what it does that if I already have 4 zones in here in the second case, top right case, and add a third line to it. Okay, so third line gave me 3 more. Okay, next line gave me 4 more zones. Next line will give me 5 more zones, and so on. So if I integrate out that kind of thing, I'll get features like here. The n number of zones will become some n1 square because n0 is 2 over here. So it grows quadratically for large value of this decision boundaries. Okay.
Hello.
So, yeah, hello.
Hello.
Yes.
So, just to clarify, what does this 0, 1 means? Can you tell me once again?
Okay, so I'm just saying. So, okay, thanks for pointing it out. So these 0 ones that I have written, so like in the first image, if you see, 0 means you are on the positive side of the decision boundary. 1 means your negative side, or the vice versa. You choose a convention. It just says there are 2 different sides of a decision boundary. Okay. So what it says
there
that
is nothing to do with label, right? This is not labels.
This is not the label, no. But
Okay.
I'm trying to say, okay, so yeah, this one I was missing. So what will happen is that these numbers that I have written is just says that one side, this is the one side of the decision boundary, this is the other side of the decision boundary, and we can choose a convention that the positive side, positive means the linear combination, this line depicts a linear combination of features. So when the linear combination of feature is 0, you don't get the line, which is a decision boundary. But when the linear combination is positive, you're on the one side. Linear combination is negative, you're on the other side. Right? That's how the boundary comes. 0 is the boundary. So here I'm saying use this binary digit 0 and 1 to say that one side is 0, one side is 1. And for the sake of simplicity, just whenever you see positive, you say 0. When you get negative, you say -1. Okay. So different lines will have different things. So each zone, okay, will have its unique code with regard to all the decision boundaries. That each zone, that whatever number of zones that we are dividing it into, each zone is either on one side of the decision boundary or on the other side. So if you have N1 features, so not N1 features, you have N1 number of neurons in the first layer, then what one can do, that I can write an N1 bit sequence, okay, and convert that into integer. That's the later part. So N1 bit, using the N1 bits, I can define uniquely each zone, because I know about each zone which side of the decision boundary they are. Okay, so as we increase the number of zones, number of decision boundary, the number of zones kind of increases initially by 2 to the power n1, as you know it should, but that is a total possible number of zones that, the integers that could be represented. But that many zones are not there in general. So if you keep on increasing n1, okay, 2 to the power n1 is all possible number of zones you can label using n1 bit, but that many zones do not exist, because as I said, that whenever n1 is larger than n0, it has a power law growth. It doesn't have exponential growth. But it is true that no matter which zone you are in, like here you look at the 7th guy, by using 3 integers, I can uniquely tell, okay, which side of which line it is. And of course, one of them is missing here. So if I just say, now I can't remember, out of 8 possibilities, one of the possibility is missing in this 3rd image. And I haven't done the labeling in the 4th image. There are total 16 possibility, okay, but only 11 zones exist. Okay, so since the number of labeling possibility is more than the number of zones, each zone has a unique code, but each code doesn't have a zone associated with it. Okay, so so this is how the first layer works. First layer task is to uniquely label, first of all, subdivide the feature space into a lot of subspaces. Okay, lot of zones. Okay, and now these zones are labeled in some way using that n1 bit thing. You don't have to label it. That's just for understanding in this particular discussion. Now, what does second layer does? Okay, so second layer, the neurons in each layer, it says that take zone, take this particular zone and this particular zone and combine into one. Okay, so any union or intersection of these, any combination of zones is what is done in the second layer. Okay, so it takes the output of first layer, and any feature, any point, any data point is either in any one of the zone. It can't be in more than one zone. Okay, so it is in some place, the feature point. Let's just say this is your feature point here. Okay, sorry, my pen. Okay, so this is my feature point in the last image. Okay, so this has, it is in particular zone. It's not in all other zones, but this is defined as, let's just say, positive side of this green line, negative side of this light blue line, negative side of this purple line, and positive side of the red line. So it has unique location. Although when I describe these 3 guys, I define the zone uniquely. The 4th information about which side of the red line is superfluous in this particular example, but it may not. Okay, so some of the cases, some other information would be superfluous. Okay, so but what happens that each zone is uniquely labeled by, in this particular last example, by 4 bits. Okay, which I haven't written. Now, coming back to this thing, so second layer, what it does is to combine these zones using union or intersection into some higher level shapes. Okay, so basically we are looking at a complicated, trying to emulate a complicated decision boundary, which are not planes. So first job is the layer 1 is to divide into these many zones. Layer 2 now start combining them in certain manner, and then further layers, what does they do? They combine the combinations in different ways. So what are the combinations that are allowed? Unions and intersections. So all the neural network does is basically a complicated way of doing unions and intersections. So that's all. We keep on going. So at the end, the final shape, whatever we have, it's going to be a very complicated shape depending upon how deep network is and what kind of data you have. But one is very important thing, that whatever final shape you get, this is some union of the basic shapes that you find at the end of first hidden layer. So your first hidden layer is really important. This first hidden layer is going to be really important in that sense. Okay. Anything else is just a union and intersection of this. At the end, whatever I get at the output will say whatever this n0 dimensional space was divided using the first layer, a particular combination of that is my zone of interest. And that's how the training becomes. So training means that since I keep on changing the decision boundary, each of this n1 decision boundary. So what I'm doing, I'm evolving the shape, rather all these lines, I'm evolving. That's my learning part. I'm evolving that how to subdivide my feature space into zones. That's my first layer learning, and all the subsequent layer learning is that which combination of these basic divisions, first layer divisions, emulates my final answer. Okay, and the final answer is more complicated, then you need more layers to capture that.
I have a question.
Yeah.
So here each line, basically we have add each line means that we have add more features into this, right?
Yeah, every single, no. A feature is 2-dimension. Feature is 2-dimension. Okay, so I have x1 and x2. Only 2 feature is there. So my n0 in this case is 2. Okay, n1 is number of neurons. Okay, number of neurons in the first layer. Okay, so that is 4 here. Okay, in this particular case,
okay,
it is 4. So number of lines is the number of decision boundary. So each, I say again, so this is the first layer is number of features. Okay, n1 here, this is here. This says how many decision boundary you took in the first layer. And with that decision boundaries, you are dividing the feature space into so many pieces. And here is the estimate of, this is the estimate. So features is constant, number of layers, sorry, number of neurons in the first layer is what I'm changing in this particular discussion. Okay. So if we have more number of neurons in the first layer, I have longer bit size, right? So when I have only one decision boundary here, then I have 1 bit. Here I have 2 decision boundaries, so I have 2 bits. Here I have 3 decision boundaries, so I have 3 bits. And in the last one, I have not written. Okay. And so basically your layer 1, so I'll repeat this again. So layer 1 divides the feature space into suitable number of zones, which is decided by these 2 numbers. Okay, depending upon which zone you are in. Okay, depending on what, if your n1 is much larger than n0, then it is n1 power n0 is roughly how it goes, the number of zones. So number of zone is important, that you want to really learn it, so your n1 has to be large. And then as this image also shows, that your n1 is large, and then n2 and n3 in a subsequent layer must reduce. Okay, and at the end you have to make some decisions. Here it is just in this particular picture, just one output, but you could have the softmax. Actually, final answer is only one answer, and if they are multi-class classification, even then the final answer is that which class is it. So using some softmax function, we try to get that. Okay, so coming back to here, so I have divided all these things into, or the first feature space into many zones. Then using the second layer, I'll combine them in various ways. And then you see, each neuron of the second layer is one particular combination of the zones that you have found at the end of the first layer, first hidden layer. So at the end of first hidden layer, you have a bunch of zones. Then at the end of each neuron of the second layer will take a particular combination, union or intersection of this, and then give an output. Okay, say take this shape. Okay, so this will click if the original, if the data is in any one of those selected zones, then it will click. And likewise for other neurons. The next layer, it will combine either using union or intersection, all these shapes that you get at the end of this. So if you remember when CNN was discussed by Swagata, she said that at the first layer, your image or this thing learns only the edges like vertical edge, horizontal edge, slanting edge. That is the basic thing it learns. Then we combine bunch of edges, small edges. Okay, a union of bunch of edges might look like a nose or an ear and also or an eye. So that's what you learn. Then at the next level, a combination of all these things might look like a face. Okay, so that's how you build. Each layer is a combination of outputs of the previous layer, and each layer and everything is made of even basic and even basic stuff. Okay. So at the end, whatever the zone that I get is basically some union or even the intersection, I should say, of all the basic shapes at the end of the first zone. Now let's come to what kind of data we have. So if I'm handling an image data, then we have to look at some basic numbers that comes into the ANN. So typical ANN that we have, so not for image data, but other tasks, the N0, the number of features, are typically 100 features or 200 features are there, typical ANNs that we use. And then N1 level, I have 200 to 500 nodes in the first layer itself. So that kind of gives, this kind of networks gives about, roughly 1.5 lakhs trainable parameter with few hidden layers. Okay, so these many parameters needs to be trained. But if I have a typical image, like this is not a very huge image, this is 100 pixel by 100 pixel, that means my N0 itself is 10,000. So if my N0 is 10,000, my N1 typically I take larger than N0. So I'll take 2 times 10,000, that's 20,000 nodes. And if I take bunch of these things, few layers, then I will have a billion trainable parameters within a few hidden layers. A billion is a huge number. Okay. So an image has too much information. Okay. So if I try to do this image processing or identification, whatever task we have, using an ANN, then I need huge trainable parameters. So we need to do something difficult to train even for a moderate size. 100 cross 100 is a moderate size image. It's not a, typically we have few thousand cross few thousand pixel. That's just several million pixel in one image, and that's already out of reach. Okay. Now, so what we need to do, okay, so we need to exploit the spatial proximity of the features. That's very important. Okay. Sorry. What is the spatial proximity would mean? It means that the pixels that I'm considering are not random. This is a spatial sequence. There's a meaning to left and right. There's a meaning to up and down. And there's a meaning to the proximity, that this pixel is closer to that. But if I just convert a 100 cross 100 pixel image into a vector of size 10,000, so the information in this entries are not there, that which one is closer to which one. I might have that Vn is closer to Vn minus 1 and Vn plus 1. So kind of one-dimensional proximity can still be managed using a vector representation, okay, vectorization part. But a 2D image will have more than that information. So that information, which is a part of the information contained in the image, is not contained in if I vectorize that. So the things that I want to identify is kind of destroyed if I make it linear. Okay, a feature of length 10,000, feature vector of length 10,000 if I make here. Okay, so that information is kind of gone. So I have to exploit that. And plus this network is too huge to train. It's that people have done this kind of stuff. You can still make it work. Okay, it requires too many trainable parameters. It takes time to train, but what I'm trying to point out, it is still doable. Okay, So there you will find on internet some information about what called MNIST data, which is 28 cross 28 pixels, handwritten digits. So this is, if I'm not wrong, is 784 or something like that. Okay, 784 features. So 784 is not all that big, and people have written networks, ANNs, to do these things, and that it does a decent job, but it takes large number of trainable parameters, large number of memory to store, large amount of memory to store the network itself. And then, of course, when that many numbers there, that many operations has to be performed to make a decision. So it's slow also. So if you have low number of features, so a low number of parameters, then I can do the job quickly. And of course, I'll be identifying things more clearly, because I will be exploiting my spatial features. Okay, spatial features I'll be exploiting. So let's look at the sequences and all these things, what we have. So a feature vector, okay, what will happen? What happens in a feature vector is that the index of a feature in the feature vector has no physical meaning. But I can store the house number of bedroom in the house as a first entry or the second entry. It has no meaning either way. But whatever I choose, I have to stick to that. It's not that in one data instance it will be second entry and in the next data instance it will be first entry. That's confusing. But it could be anywhere, provided it has a fixed value. Okay, so that, but because it has no specific meaning where in that vector the number of bedrooms set. Okay, in the feature vector. So the statement I'm making is the index of the features in the feature vector has no physical meaning. Okay. Now for the spatial sequences, the index of an entry in the spatial sequence has no physical meaning again. It could have been anywhere. Okay. Like here, one-dimensional sequence that I have drawn over here. It could be anywhere. Okay. Provided, from instance to instance, that is constant. Okay. Next comes the relative index value of two features in the vector has no physical meaning. Relative means, suppose the first entry is the square foot and the third entry is the number of bedroom in one example. And if I change the example, if I change every data, that first entry is the square foot and second entry is the number of bedrooms. As far as the entire data set has the same thing, it has the same meaning. So relative values of index has no meaning, okay, for the feature vector. But that is not true for sequences. Okay, because where is one particular entry may not matter, but the relative positions of two entry matter, because that's what sequence means. How far to the right, how far to the left, and there is a sense of right and left. Okay, so that is the first difference you see between the feature vector and the spatial sequences. Next comes the element of feature vector. It basically forms a set. It has no additional features. Okay. So all the elements I can, and that's why index has no relative index also has no physical meaning. The elements of sequence form a metric space. Okay. And a distance between two entries can be measured. How many steps to the right and how many steps to the left has a meaning. While for the feature vector, it doesn't have meaning, because the two objects are completely different objects. Okay. Two entries are completely different objects. A set is symmetric under permutation because it doesn't have any additional features. So a set is symmetric. So in which order I could have done the indices doesn't really matter. But here, in the case of spatial sequences, it is symmetric only under translation, because relative positioning I have to maintain. So there is also invariance, but that's a translation invariance. Okay. So there are different symmetries in the thing what we do for ANN and things that we do for CNN. Okay. So usually this feature vector is used in ANN, and spatial sequences for that I will use CNN. Okay. So if the set is symmetric under permutation, that's we need to feed all the elements of each of the neurons. Okay. We need to feed all the elements to each of the neurons, like in ANN, right? the entire feature vector here is fed to each of the neuron. Okay, that is a necessity. Okay, I have to do that because the full thing is one piece of information. But since set is symmetric under translations only, that means I can feed, okay, a subsequence to the neurons. Okay, a subsequence is also a sequence, but a subset doesn't have all the structure because it has a missing information. So the whole idea of learning sequences is to learn the subsequences and build the bigger sequences as a union of the small subsequences. That's where we gain. So one feature vector here, one feature vector if given, it's one instance of the data. Okay, just one data. But for the case of spatial sequences, all the subsequence of a given, all the contiguous subsequence of a given sequence are the valid instance of data. Okay, so I can feed in the subsequences. So the case of 2D images, we can just say, so vectorization, what happens if I take a 2D image and make it into one vector? The 2D image data needs to be vectorized to be used for any ANN. Okay, so this respects the symmetry and the permutation, but not under translation. For example, a shifted or the translated image of a cat is still an image of a cat. But if you do a translation, the vector completely changes. Values in the vector changes. It's not just the permutation. So we need to implement a translation over there. And for the subsequence, a fixed site subsequence in this particular case here, like just say this window here. Okay, this is called a window, and this subsequence is treated as a feature vector. So what I do, instead of taking the whole image, I take this subsequence, some sub-image, and then vectorize only this part because I need to use it into ANN, smaller ANN. Okay. So what I will do, I'll take a subsequence and I treat it as a feature vector, and a simple ANN style task is performed after the vectorization. Then what we do, then we slide the window. Okay, so the initial window that I had, okay, is moved somewhere else. Okay, and I repeat the task. The amount by which this window is shifted is called stride. Okay, and treating the corresponding subsequence, so we need to we treat the corresponding subsequence as a new feature vector. Now, important thing is if my initial slide window is here, my next step window would move by one step to the right, or one step to the left, or down and up, or two step or three step. They can be overlapping. There's nothing wrong with that. Okay. And of course, the weight metrics corresponding to the subsequence are, we are going to call that either a filter or a convolution kernel. We'll look at this in the example. Okay. So this is how, yeah, any question?
Hello?
Yeah. Yeah.
So isn't the overlapping is important because let's say if they don't overlap, we can miss some important sequence.
Yeah. So what I'm trying to say is that non-overlapping, okay, is a special kind of treatment sometimes required. Okay, but not here. Usually we require the overlap such that we have each and every structure captured. Okay, so in CNN, overlap is always is used. So size of the stride is typically 1. Okay, and while the minimum size of this convolution kernel is 3. Usually we take the odd number. So suppose here's the target. Suppose this is the target pixel. Then I take equal number of the pixel to the right, to the left, to the top, to the bottom. So I get this 3 × 3 guy is the smallest I can have. I can also have this 5 × 5. Okay, so I can have this. So I can have 3 × 3 kernel or the 5 × 5 kernel. Call it kernel or a filter. Both names are used. And when I'm shifting it, so I'll just move this guy, okay, the central guy by one step in any direction. Okay, so that I can do that. Next step, this will be here, and likewise I can have filter around it. So of course, most of the tasks we do that, but sometimes if the features are not that fine, if we know that features are not that fine, then we may want stride to be slightly bigger. But usually we don't make them non-overlapping. Usually we always do the overlaps. Okay, in the features. Okay, So as I say, typically we have features of all odd size. So we have 3x3 or 5x5, even higher sizes are used. There's nothing wrong with using the even, okay? It just uses a certain internal rule. You decide when you divide even how many to the right and how many to the left you will have, including the guy. Okay, so you can have that to the right, I'll take, n by 2, and to the left, I'll take n by 2 minus 1. Okay, and including the central guy, it will be n by 2 again. Okay, so that's a typical rule one can use. Okay, and with that, one can do a sequencing. So convolution part is basically that I took this entries of this box, okay, vectorize them into convert them into a vector of size, in this particular case 3x3 will give me 9. Okay, so this 9, and then I have a weight matrix. Okay, so each one is multiplied by a weight. Okay, 1, W2, and all that, summed up and added with a bias. So that is what a neuron does. Okay, it takes the feature vector, multiplies each entry by some weights, and then adds a bias, and then passes it on to a sigmoid. Okay, or whatever other activation function. So let me call it alpha. So alpha is the activation function. It could be sigmoid function, it could be ReLU function. Okay. So appropriate choices can be made. So this is a convolution that we do. But I just wanted to make one thing clear over here, is that what that stride and convolution has to do. So if I take the stride, so stride, if more than one, then basically it reduces the size of the output image. It's kind of, if the stride is 2, the size reduces in each direction by factor 2, and so on. So what does this, given an example of one-dimensional sequence, not two-dimensional, what would be a filter look like? So my convolution filter could be like this written over here, which is -1, 0, 1. What it does, take the central guy, say f of x, x is an index, okay, and take a previous guy, take a next guy. So this is my size 3 filter. Then I multiply the first guy with -1, middle guy with 0, third last guy with +1. Okay, so that will give me fx plus h minus fx minus h. And if the weight factor instead of +1 and -1, it was plus w and minus w, then it will multiply by w. If w is equal to 2h, that's basically a derivative in the x direction. Okay, so I would be able to find out numerically the derivative in a given direction, even in the image if they are two-dimensional. Okay, we'll see the example of that. And so what I need now, I guess I'll stop sharing. Yeah, okay, so before I stop sharing, this thing has been discussed, but just for completeness, other than the convolution, to reduce the size of the output image and capture the basic feature, what we do, there's a two kind of pooling we do. We do max pooling, that we choose a subsequence, okay, say in this case I'm choosing 2x2, and replace it by the maximum value in the next image. Okay, so that's called max pooling. Another is average pooling. I take that sequence, I could take say 2x2 or 3x3, and take the average of this and replace in the next image. So what the first example, I'm saying 2x2, it will reduce in each direction the image size by factor 2. This will reduce by factor 3 in each direction, because for every 3 pixel you have 1 pixel. But here I'm assuming, usually what happens, the pooling you do, the filter size is same as the stride. Okay, but if you can do stride equal to 1 and filter size whatever, then it just gives you a smoothened image. Okay, in the case of average, it gives a very blocked image, kind of more pixelated image in the case of max pooling. But we usually do pooling when I want to reduce the output image, because if you remember, the CNN architecture is roughly like this, what Swagata has said. Some input data is there, then you have convolution layer 1, then you do the pooling. Pooling could be max pooling or the average pooling. Then you have convolution. So from here, the image retained side, the moment you use pooling, it reduces. Output of the pooling will reduce. Then convolution keeps roughly the same and pooling reduces. Then convolution keeps roughly the same and pooling again reduces. And then after, when I have a larger number of channels and less size of the image, then I go for what's called fully connected layer, and then I go for output. This is a typical structure of a CNN. So what happens, the image size decreases if it processes, okay, but the number of channel increases here. Okay, so initial image might be the grayscale image, so they just have one channel, but whatever size it has, the pixel size. After convolution layer 1, the pixel size is roughly the same, okay, or exactly the same, but number of channels has increased here. That is denoted by the thickness of this blue box. Then next I do pooling. Pooling will reduce the size of the image, but increases the it may or may not increase the number of layers. That's again a choice. Usually we don't increase the number of layers. Now from here I do a convolutional layer which keeps the size same, but number of layers increased. Then we do pooling, which reduces the size and number of layers are kept same. Then we do CV that keeps the size same, but number of layers are increased. And then pooling will reduce the size again, but number of layers are increased. And then if the size has reduced to 1 or 2, okay, then we simply give that to a fully connected layer when the numbers are really, really small. Okay, then it goes to a fully connected layer and the output comes. Okay, so that's the basic CNN structure. So since I'm on this slide, let me talk about this little image that I have drawn over here. So suppose you're talking about a face, which is kind of depicted here, this part. Okay, so a face is, since your CNN will have this strokes, that strokes, this lines, that lines in first layer, and then combination of those lines will be an eye. Okay, and combination of some lines will be eyebrows and all that. So here's the image, and using which I trained. So it says yes, if I got 2 eyes and 2 eyebrows, it's kind of face. But it doesn't care if the 2 eyes and 2 eyebrows in this is appearing in this form. Okay, the relative positioning need not matter. If you are just saying how many eyes, how many eyebrows before I say it is a close-up of a face, then even this will satisfy the same criteria as this one. Okay, so if you, to make sure that this is the face and this is not the face, I have to have deeper network, which says not just the eyes and eyebrows matter, the relative positioning into a face also matters. Okay, then your deeper layer you will require, which will combine this guy in a particular way to make a face. Okay, a face-like structure that it will, which again you have seen how Swagata has shown. It's some of the example of CNN where the first few layers we just did the strokes. Then after some layers, it kind of captured the nose and the ears and the eyes. And if you stop there, then even a Picasso's painting like the one I have kind of emulated over here, that will also look like a face. Okay, but that's not the face. That's just pieces of face randomly thrown into the onto the canvas. If I have to say it is pieces of face thrown on a canvas rather than a face, then you have to have an even deeper understanding. So it's a deeper network which will also learn the acceptable relative positioning of the basic elements like eyebrows, eyes, nose, mouth. What is the relative position? Okay, so here I will.
Hello.
Yeah, hello.
Here in CNN, there is two kind. In the two portion we have weights, right? In the filter we can give weights, and also the in the fully connected layer we are with, and
yeah,
while training we are learning the both, right?
Both. Yeah. So
Okay.
what the first layer will say is that all these finer features it learns. Okay. Second layer will start to put those finer features into kind of some shape. Okay. But every time when I'm doing pooling, the reason for doing pooling is to actually reduce the image size. I can do it two ways, either doing the pooling or while doing CNN, I take the stride other than 1. Okay. So what usually people do is that don't do the stride equal to or other than 1, but you use kind of a average pooling or the maximum pooling, depending upon the case one can use either way. Okay. And then every time you increase the channels here. Okay. So you different combination of the same thing you store, that's the number of channels, but the number of features at each the increase. So this is the original features, the first one, but each layer is an input for the next layer. Output of each layer is the input for the next layer. So if I'm considering any layer, the output of the previous layer acts like a feature. Okay. So if I'm studying, say, this CV3, then output of P2 is like a feature vector, a feature image. Okay. So I want it to be smaller because the next thing I want to have smaller. So I want to reduce it, but I also want to store, not lose the information. So I put it into different channels. And when it becomes the size becomes small and the channel becomes sizable, then there I do the fully connected. And there are certain CNNs that people have been working on, which doesn't have a fully connected layer. It has at the end also a pooling layer. A couple of pooling layer does the final thing. And then you, depending upon what kind of task you have, if you have a classification task, multi-class classification task, if you have, then you use a that many dimension softmax function. Okay. So here at the end, accordingly, that many layers we try to create. Or like if this feature came, then put a part of ANN over here. So that's a mixed architecture which has CNN as well as ANN. But the fully connected layer is an ANN. You don't have to have this, is what I'm trying to say, depending upon what kind of task you have. For example, if your data is only fixed size images, then this works fine. But if your image size is not fixed, then each of this convolution layer will return a different size image. And at the end, okay, at the end, when you're going for fully connected layer, just before fully connected layer, the size of the image will be dependent upon what is the input size image. Okay, so that is unwanted. If you want same network to work on a variable size image, then you should never have a fully connected layer at that. Is that clear to you? Sorry, somebody asked question.
Yes, sir. Yes, sir.
Yeah. So fully connected layer will be useful or will make sense if and only if the input images have exactly fixed size. You cannot give a different size image to this. But if your problem has variable size image, you should never have a fully connected layer in your CNN. Okay, you can just play with the different kind of pooling layers. Okay.
So maybe
At
it's
the end,
naive, but
yeah.
Let me ask that. Can you tell me that what this channels means? Like I have heard, but I
Okay,
didn't
channels.
understand.
Yeah. Okay. So channels. Okay. First of all, I'm saying that image is one channel, but image could be three channels: R, G, and B. Right. So image itself is not a 2D image. It's kind of three layers of 2D image. Right. So I'm doing the convolution and returning one number out. Okay. So I did this convolution thing here. So I did convolution and I returned one number out. So convolution is like an ANN. Okay. So it's an ANN. So let's just say 1, 2, 3, 4, 5, 6, 7, 8, and let's put me 9. So this 9 guy comes to 1, right? All of them are connected. Okay. And if this is a ANN, then that will look like one channel. But suppose I have this guy also. So this is the second channel because it takes a different linear combination of these things, a different linear combination, and returns me second image. I want a third guy, third channel. It takes yet another linear combination and returns me third guy. So I took these many features and returned 3 numbers. So 3 channels are there. So you give me one black and white image. I converted into 3 layer images of same size. That's what convolution will do for me. Okay. Where do I gain? I gain because my ANN feature size is 9 over here. No matter size of the image, original image. My filter is 3 cross 3. So my ANN that I'm using, or whatever network I'm using, it has not more than 8 weights, 9 weights, and one bias. Okay, plus B. I always have to do. Okay. So only 10 real numbers and used over and over again. So my number of parameters reduces drastically. But that is for one channel. For the second channel, again, I have 9 plus 1, 10 guys. And here again, 9 plus 1, 10 guys. So one image I took, one layer image, and using this filter with only 30 parameters, that 3 channels, one channel means 10 parameters, 3 channels means 30 parameters. Only with 10 parameters, I created another image, which will capture different kind of features in that. Okay, so you will appreciate this more if you open the material I have given. Unfortunately, I can't share. My laptop Zoom has died, and I realized only now. So so let me first stop sharing. So how do I stop sharing? I go to Zoom and I say stop share. So it stopped sharing. Okay. So can one of you who has your system installed, the 2 files that I sent, one of them is called filters. Can you please open that file and share the screen?
Hello.
Yeah, hello. So
Yeah,
who is sharing? Arun. Arun decided some. Yeah, so please go ahead and do that.
Yeah. So I'm finding, where have you sent these files? We have got some mail.
I have sent to Arun, and Arun has uploaded onto the website.
Okay. Just 1 second.
Yeah, it is on the website. Just check the attachments in the website.
Yeah. Right. So these 2 files, right? You can see my screen.
Yeah, I can see. Okay, so open. So the CNN.pdf is this particular lecture that I was doing.
Yeah.
So please open filter thing that you open. So open Jupyter. Okay. So you can run the first thing, first cell that's just loading all the libraries. So second cell defines a 2D Gaussian where the x0, y0 is the position of the center, and sigma x and sigma y is the kind of variance on the x and y direction. Actually, the way it is written, the x and y are named in exchanged manner. Okay. And so B is just a matrix in the third entries. The B is a matrix with zeros of size 50 and 50, and that will be converted into an image. So what I'll do, the next thing, which it resets the value of image by calling Gaussian function several times. So what it does, 80 times first Gaussian, which is centered around 2020. Can you select the number one by one? So first Gaussian has the amplitude 80. Its position is around 2020, and is in the first in the row and column direction, it is size 2, and size 4 is the variance. So if you change the columns, that is the x direction, it is a more expanded size 4, and the different rows, across the rows, it is size 2. Next Gaussian is 50 amplitude 50, and it is located 3010, and size is 33. Last Gaussian is size 20, height 20, and it is some position 38 and 48 and 30, but its size is very, very small, and its height is also very small. To which I added some random number. Okay, so you can run this thing. A random number height is very, very small. Then you say plot. Okay, so this is what image looks like. So you can just see the highest guy is near 2020, which is a size 80. Then to the left and bottom, you have size 50, and in the right size bottom, there's a very small Gaussian. Suppose this is the image. Okay, and I need to do processing. So what I do, I define my filters. So there's 5 filters defined. So FH is a horizontal derivative. Okay, so if you just see, it is left to right. That means from column to column, when you move, it says -1, 0, and +1. Then same is repeated in all 3 rows. Okay, FV is just the transpose of that. It means the first row is -1, second row is 0, and third row is +1. Okay, so when I'm moving from top to bottom, I'm finding a derivative in the downward direction. Okay, FL is a left slanted guy. Okay, so it's a derivative at a, I think it's x equal to y direction. And FR is x equal to -y direction. Okay, this is the directional derivatives. Now FP is what's called peak detector. If you just see, out of these 9 objects, everything is -1/8 except the central guy, which is 1. So what it does, it takes the central pixel and multiplies it by 1. Then it takes all the 8 pixels around it and multiplies with the -1/8. So what it means, it's a difference between the central pixel and the average of all the 8 pixels around it. That's a difference. If there is a difference, then it will say how much peak is at the central pixel. Okay. Then I just define my own 2D convolution function. Okay, so can you run the previous cell?
Yeah, this
just run so that, yeah, so that data is ready. And here, what it does, it returns an output after convolution. So this is just a element-wise multiplying and shifting the filter. Okay, so whatever filter you choose. Okay, so FT is a filter. Okay, and SX and SY is this strides. In the X direction, it moves by 1 step. Y direction, it moves by 1 step. That is the SX and SY. Okay, so this is just definition of the 2D convolution. In the next cell, okay, so I'm not describing it, that you can go ahead. Next cell, I'm performing all those convolutions. So DV, DH, DL, these are the images I get after performing this corresponding filters with step 1, SX and SY set equal to 1. Okay, now it's important to have a look at what these filters look like. So can you scroll down? Here I'm just plotting the filters. So vertical gradient, okay, if you look at the vertical gradient, you can see the topmost is -1, then 0, and then +1. The horizontal gradient is just -1 column, 1, 0 column, and the +1 in the last column. And the left slanted is when you go across x equal to -y. So y equal to x equal to -y. So on the negative side, which is going to at the 135 degrees from the x-axis. Okay, and the right slanted is at the 45 degrees from the x-axis. Okay, and the last guy is the peak detector. And of course, not last but one guy. And last is just, if I needed 5 images, I have only 5 things, so there is nothing on the last. Okay, so now we plot. So you can actually run it because it doesn't take much time. But anyway, here's the output. So here I have got 6 guys. The last guy is original. The bottom right is the original image that we just generated. But the vertical gradient, if you see, if I'm moving from top to bottom, when is the gradient positive, you have yellow. When the gradient is negative, you have dark. And when it is 0-ish, you have light green. Okay, so you can see it looks like a shadow. It captures the feature. On the second image on the top row, when you move from left to right, left to right, when you face the positive gradient, you have brighter color. When you face the negative gradient, you have a super color. So it kind of finds a gradient. Then left slanted, when you're going from the right bottom to left top, you are moving. Okay, so that's the shape you will get. And as you can see, even the smaller guy with very low height in the bottom, which has height only 20, it kinds of more visible because we are taking derivatives. Okay, and the second row leftmost, you see from left bottom to right top, I'm taking the derivative in that direction. And the middle panel in the lower thing is the peak detector. Now peak detector, you can see even the faint guy on the right bottom is visible. Okay, faint guy you can compare with the original image. Okay, so apart from the fact that it is peaked, the color also shows how much peaked it is. Okay, And if there's a darker color, that means there's a dip over there, kind of. No, if there's it's in place of the surface being concave, if it is the surface is concave, it will have darker color. Okay. Now we'll play with this again. Can you go up and regenerate the image? Okay, so this was this thing. So when I'm generating the image B, I took the noise very small, 0.1. Okay, just make it 10. Okay, rerun it and replot this thing. Okay, now you see there's a lot of noise. And you can see the amount of noise is comparable to the last peak, and hence the last peak is not clearly visible. The smaller peak on the right bottom. Okay. So we'll run the filters again. We don't have to do these things. Yeah, this is just a definition. Go down. Yeah, so this convolution part, we have to redo it. Convolution part. Just before the filters.
Yeah, this.
No, this is just showing the image. Before the filters, you have to run it. Go above. I've written here. The SX, SY, you have to reconvolute it. Filters are same. Filters are not changing, so you don't have to replot it. 18, you just ignore. Okay. Then you come to the 19, and this one you do, and you see. Okay. Now look at the leftmost guy. Since I'm getting the derivative from the top to bottom, okay, because of the random fluctuations, you will see more horizontal line because it's changing from top to bottom. In the horizontal gradient, you will see many vertical lines. Okay. In the left slanted derivative, you see a lot of right slanted line. In the right slanted derivative, you see a lot of left slanted. The worst is the peak detector, because peak detector is now picking up every random physics. Okay. And of course, the bottom right is the original image. So original image, if it is noisy, if you use a peak detector, I get this noisy image. So what I will do, what the right thing to do if the noise is too much, we do smoothing filter. Smoothing filter is very much like peak detector, but it has 0 weight in the center and 1/8 weight everywhere else. Okay, or 1/9 weight everywhere else. So what it will do, it will take all the pixels. 1/9 weight it will do. It will take all the pixels and take average and replace at the center. And if it is 1/8 everywhere except the center, then we'll take average of the surrounding is the value at the center. And value at the center is not counted. So there are two different ways of taking averages. So one can do that first and then look for the peak detection. Okay. So I think that 1/9 is a better option, because if you do 1/8 with the whole, everything becomes flat. There will be no peaks. Okay. So the peak detector will never work. And that you can check why it won't. Okay. So this is how the filters work. And this is just one output of one filter. I have 5 filters. Now using the same one image, which is just one layer image, it is just shown in the color, but actually it's one layer image. Using just one layer image, I created 5 different images, which will tell me about different features of the same layer. Okay, so that is 5 channels. Okay, so I started with one image. Now I got 5 of them. Okay, then I do some kind of pooling. The pooling happens across the layers. Okay, across the channels, so to say. Okay, so I take some information from one channel, another information from another channel, and do kind of pooling in all of it, or some other combination to get things. So that I have to decide which kind of pooling I want to do. Okay. So so any question on this? You can play with this, and you can define your own filter in this example, and play as much as you want to get a more feel about what kind of features I can generate. Even more interesting, that original image that I have generated, I just played and increased the noise. You can get different kind of Gaussians, different very narrow, very sharp, very slanted, whatever kind of Gaussian you can want to create, or any other shape you want to create, or instead of you creating a shape, you just import an image. Okay, whatever you want to do, you take that image and then perform this task. Okay, to see what this vertical gradient, horizontal gradient, and left slant, right slant, and the peak detector does. But as you can see, these filters have fixed weights. What CNN training is to learn those weights. So you don't give them, you don't tell CNN that take the left gradient or this gradient or that gradient. You say, initialize your weights to some random value. That's your filter. It's some random filter. Okay, it has no meaning. Now, whatever the output is passed through various filters and then compared with output. It has no meaning again, so it tries to learn those weights. Okay, through the whatever forward pass and the backward pass, back propagation that Sogata talked about. So using those techniques, it learns. For filters, you don't have to provide. Here, the example is that if you provided your filters, I have given only the derivative in one dimension and the two dimension things. We can have some other thing which may have meaning of derivatives, may not have meaning of derivatives, maybe have meaning of second derivative or something like that. If you want more than second derivative, then 3x3 filter will not work. You need to go for bigger size filter to have higher derivatives. Okay. So those derivatives, if you want to compute, you will be able to compute, provided they have some information. Okay. So do we have specific questions? Otherwise, you can play with this. And I will move on to one example of CNN using TensorFlow, the next thing that I have sent. This is convolution network. So I have given you this, and this can be downloaded from the website that is given here. This Americ Damien has put on this on website. Okay, and as you can see, this image shows very nicely how the convolution neural network works. It has input layer, then convolution layer, pooling layer, convolution, pooling, and sequence of that. Then locally connected layer, what's called locally connected layer, that they are talking about especially, then fully connected layer. We basically work with, in this particular example, only with the fully connected layer. Okay, then comes a description of MNIST data set. Okay, so MNIST data set is 28 cross 28 pixel images of which has value of 0 to 225. Okay, each pixel is 0 to 225. It's a grayscale image, and a lot of images are there. And this is the handwritten digit, and this has been long back. It was, this data set was generated by scanning the postal codes, and it was for the reading the postal codes. And the manual tagging, the truth tagging has been done. So we know what these digits are, and the information is stored. Okay, so idea is to learn from this. So here again, more information on this MNIST data is, the link is below. Okay, you can look at. Now cell number 1 here, it just loads all the TensorFlow and all this stuff. So if you can run, you have your own output, some error. Okay, there is the error. Okay, what did not work?
I think
Tensor.keras was not there.
You can just do Keras.
Okay.
Yeah.
Okay. I hope it works for rest of the things. And then here in the cell number 2, current cell number 2. So here you have 10 classes because you have digits from 0 to 9. And usually we define some hyperparameter. This is like learning rate is taken to be 0.001. Training step means how many epochs you want to train, how many times you want to go through the data. Okay, so that's here we have chosen 200. And the batch size. So you don't take the whole data in one go. That's also, I think, was discussed. And so you take a small batches. So here batch size is 128. And display step 10 means after every 10 steps, you display what did you do. Okay. And here the convolution filter is there. So how many layers you want? Like I was showing for 5 layers, 5 different convolution filters. So it's in the first convolution filter, it takes 1 layer image and convert into 32 layer image. Okay. And convolution 2 filters, what it takes 32 layers and convert into 64 layers. Okay. And then in the last fully connected layer, it has 1024 output entries. Okay. So here everything becomes 1024 size vector out the output, one dimensional vector. Now you can do ANN on that to give me 10 outputs, and then using softmax, I choose the which one it is. Okay. So again, you can run this. I don't know whether this. Okay. So here also you have to change because not TensorFlow.keras. You have to take from Keras. Okay. So you can get this data. So MNIST.load data is kind of inbuilt function which it downloads from. It has the information where to download, and it downloads only once on your laptop. So once you run this code once, you can use the MNIST data for any other programs or projects. Okay, so first line just loads the data, and in this particular code, it gives it a name xtrain, ytrain, xtest, ytest, because the training and testing set is already decided. Then in next one, it converts into a float because it was integer, so you want to convert into float, and then you want to divide it by 255 to convert this into a number between 0 and 1. Okay, so these are just pre-processing as they call. Okay, so you can run that part, and then next is you basically you are using the API to shuffle the data. So data is there in some sequence. Here it does the shuffling. Okay, and it kind of prefetches some. I think only 5,000 of that it is taking, and divided into batch size of 128. Okay. Now comes your actual TensorFlow model. So this is a class you generate. So model is inside TensorFlow. So you take derive your own convolute from there. And here the first layer is a convolution layer, which is Conv2D. It takes 32 filters. Kernel size is 5 here. Okay. And activation is ReLU. The ReLU you have seen, it's a rectified linear unit. So when the value is positive, it returns the value X. When the value is negative, it returns 0. If you use leaky ReLU, then it returns some negative value as well. But here, ReLU is used. Okay. And then it does the MaxPooling, which it's size 2 and stride 2. That means the image will be divided in two, like the length and breadth both will reduce to half. Okay.
Hello.
Yeah, hello.
Here you have told that there is some shuffling done. So
yeah.
Here, so my question is that what is
Why?
shuffling like?
Yeah. Okay. So what it may happen that in your data internally, that you while storing, you provide all the digit ones, all the instances of digit 1, then all the instances of digit 2, and so on, right? So data may be stored like that, but you don't want to pass one kind of data in one batch to the network, because it will think that there is no variation in the data. So in one go, whatever batch size is, that must have as much variety of data as possible, each batch. So the one way to ensure that each batch has all kind of data that is trying to learn, you shuffle the data, shuffle the deck. Okay. Of whatever data sequence you have, you just shuffle it. Then any randomly chosen, or rather not any 128 size piece, okay, would be well mixed. So that's the purpose of shuffle. Okay. It's always advised to shuffle, even if your original data is shuffled, people kind of as a safety measure shuffle it again, because you don't know if the original data was not completely shuffled. Okay, that's just more. Yeah.
It means if I have, like, let's say 50,000 data, then it will make, let's say, 500 of batches, and each 500 batches have all varieties of thing oil shuffled.
Yeah.
Okay.
So here in this thing, there are 3 layers. Sorry, 3 convolution layers. So first convolution layer, then MaxPool 1, which is the maximum. It just takes the maximum of the 2 + 2 and replaces it at that, and then take the stride 2. So it reduces the 28 × 28 image into 14 × 14 image. Okay. Then comes next layer, which has 32 filters, of course. It has kernel size 3. Okay. And activation is again ReLU. And so image size remains same. And then MaxPooling 2 again reduces it from 14 to 7 × 7. Then it flattens it. So 7 × 7 is only 7 + 7 is only I think 7 × 7, or maybe some other number. Maybe I'm missing. It's not 7 × 7 because 64 channels are there, and 64 times how much is 1024, 128. So 2, 2, 2, and 2. So 16 times this. So yeah, so that is not 7 × 7. That's actually 4 × 4. And why it is okay. One thing I forgot. When you are doing convolution, okay, and not doing padding, your image size anyway reduces. You learned that from Sogata. Sogata talked about the padding, I believe. Yeah. So when you have 5 × 5 kernel, you already lost 2 size. Okay, so 28 became, I guess, 26. Then it became 13. And then 13 became, I think, 11 or something. Then, or even lesser. Maybe I'm not doing the counting properly. Oh, just a moment. 28 became 24. Yeah, 4 it will lose. And 24 will become half, which is 12. And 12 will become 10. And 10 will become, actually, after dividing 4, and the 4 square, yeah, 4 square is 16, times 32 will give me, after flattening, 1024. Okay, that's my data. And then you make a fully connected layer, the dense layer. Next line. After flattening the output, okay, you make a dense layer, and then you apply a dropout. So dropout is one way of regularizing. So one way to regularize is to add the square of the weights or the linear modulus of the weights. That's called L1 regularization or L2 regularization. Other way to regularize is you randomly drop out a certain percentage of the neurons. Okay, and here in the last layer, in the dense layer, it will happen. So what it means is that because there are so many parameters, by randomly switching them off, you are trying to say that it's not overtrains. Okay, so that's the purpose of dropout. And every time it does it differently. And the output layer, then it does dense and then number of classes. So it will convert into the number of classes. Okay, and then this softmax is performed on that. Okay, the actual thing, when you call it, it just takes reshapes the data, because data comes as a linear thing, into 28 plus 28, then applies convolution, then MaxPool 1, then convolution 2, MaxPool 2, then it says flatten, then it says fully connected 1, then dropout. Okay, if when training is training, you drop out, and then you take the output layer. Okay, and at the end, you do softmax, x equal to softmax. So that is your return x. It returns the x, which is a size 10 number. Okay, a vector of number size 10. Okay, so that's your output, and then you define next thing, cross entropy, the loss, because that has to be minimized. Okay, then you define another function called accuracy, how you compute the accuracy. Okay, so this I'm not going into because ANN has the same thing. Okay, and then the last one is you actually run the optimizer. Okay, so here it is training. This is again function to run optimization. So here you're defining function. You're defining optimizer. You're using Adam optimizer that is defined in the previous cell. Okay, and then you run it. Okay, so can you come down? Okay, so when you run, it prints every 10 step. Okay, every 10 step it prints, and it does very quickly. And you can see accuracy keeps on increasing. Okay, sometimes it goes down. Okay, so then you do a full test. That is the intermittent test was doing. So the cell 9, if you run. Okay, so your accuracy is 97%, but it can be more. Okay, it can be more, and then you import the PLT for plotting, and then you say 10 images you are just going to print. Okay, and it also says what it was. It shows the image and says what is the prediction. So you can see it was a 0. Okay, that's a 0 prediction. The next image looks like 6. It is predicted 6. Next image looks like 9, predicted 9. Okay, the next image looks like 0, predicted 0. So I printed here 10. Okay, and so you can print some smaller, larger number or different part of the test data. Okay, to visually confirm that it works. Okay, but here a CNN is used, and this example you can just check on that link I have taken. On that same link, you will find examples of ANN as well. The same task is done using ANN. Okay, and CNN, and you can also see how many parameters you actually used to do this task. And CNN wins because it can get because it uses this feature of the 2-dimensional sequencing. Okay, or called the translation invariance, which is the symmetry of the data. It uses that, and a shared weight, like each window has the same weight. And once the job is done, then using the optimizer, the window weights are changed. That means the filter is updated. So next time the same filter is used, same set of filters are used in the same sequence to get you the answer. So slowly you start to learn that. And different filters start to capture different features, and the sequence of features, okay, will look like a particular number. And then if all those checks are together there, then it says, yeah, I found a number that looks like 3 or a number that looks like 2. Okay, that's how it predicts. But on these images also, you can run the things that I gave, the peak detector and the slanting, all these things. Okay, just for fun, just for playing, you can do that. Okay, on these images. But I'm saying that you can also look at what kind of filters there are by printing all those weights. Okay, the weights that it learned, you can print those weights. You can access that. You will have to see how to access that, and can print that. At each layer, convolution layer 1, what was the weights? Convolution layer 2, of course, it's not just weight. It's 32 different filters of size 5 plus 5. So it is 5 plus 5 plus 32 numbers that it is. Okay. And you might want to look at that. If here's the image, what happens after convolution 1, and then you print it. So then you have to run those functions that you have done and print at kind of print the image after every transformation. And that will also give you a better understanding of how actually the trained, I'm only talking about the trained network. At the end, instead of looking at the final result, you can also look at, here's my input image, and after passing the layer 1, I get a set of 32 images, what they are. Okay. Then after passing the layer 2, there are 64 images, what they are, you can ask. Okay, they are smaller in size, but what do they look like? Okay, you can print them and see. So I haven't done those part of the codes here, but these are the things you can do on your own to play more and to dig more into this. So that's all from my side. And if there are questions, we can address. But first you have to play with this. Anybody having difficulty running these codes? Because that's more important. We don't want this to have problems in the main school.
Hello.
Okay. Yeah. Hello.
Hello.
Yes.
Can you explain how pooling layer works in this case?
How what?
How pooling layers?
Okay, pooling layer here. Okay, so can you go to the where we set the networks?
Okay.
Okay. So here, MaxPool 1, for example, what it did, it took a 2x2 region, okay, and looked for what is the maximum value. Okay, and it returned the maximum value. That's the MaxPool. And in this particular case, only the MaxPool are used. But you could have used average pool, which will take 2x2 filter, replace it by the average of those 4 numbers. But here MaxPool is used. And then the window is moved by size 2 to the x-axis. Okay. And then after done, it is moved 2 steps to the down, and then same thing is repeated. So stride equal to 2 means that move 2 steps to the right, 2 steps to the down. But I could, instead of giving stride equal to 2, I can give stride equal to 2, 1. Okay, 2, 1 means for the rows, you make 2 steps. For the columns, you make 1 step. Mixed strides is possible. Okay, filter size, I said 2, which means 2x2. Okay, and right above convolution, I also said kernel size 5, that means 5x5. But I can give, unequal size, non-square shapes as well. And stride for the convolution is assumed to be 1, 1, but anything else you have to give it. Okay, so if you don't say anything for the MaxPool, it will not have stride 2, it will have stride 1. Stride default value is 1 in TensorFlow implementations. So it basically stride equal
Okay,
to
thank
2
you.
means, yeah, stride equal to 2 means the image size reduces by 2. And if you know, since the kernel size is 5, okay, a size 30, a size 28 image will have so many instances, but it will, the next image will be the image size minus filter size plus 1, or rather image size plus 1 minus the filter size is the next thing. So 28 guy will become 24. 28 plus 1 is 29, minus 5 is 24. Okay. So 28 plus 28 will become 24 plus 24. Then max pooling of 2 plus 2 and stride 2 will make it half on both directions, so become 12 plus 12. Okay. Then you have kernel size 3. So 12 plus 3 is 15. So minus 1. Sorry, 12 plus 1 is 13, minus 3 is 10. Okay. So 10 cross 10 images. From 12 cross 12, I get 10 cross 10. And then I do max pooling. Okay. So it gives me 4. Actually, it should give 5. Why should not give 4? Yeah. Okay. So it gives 5 plus 5, and there are still 64 layers. And then we flatten that layer. I think one can keep on checking what does it do. I mean, by checking the sizes at each layer. There are ways to print that. Okay. If there are more questions, can take. Okay. So Arun is leaving. Yeah. And other people have also, some people have left. So if you have questions, we can continue. Otherwise, those who don't have questions, you can, yeah, already leave.
Hello, sir.
Yeah.
So can you
Yes.
please explain the test image part one more time, like the 13th block?
Okay. Can you scroll down, please? 13th block, yeah. So test image is what it does. Okay, last one, the images. So what it did,
Yeah,
that
the 14th one, yeah.
yeah. So it passed image by image, okay, and found out the prediction. So I'm doing what? I'm just printing an image and telling what the model gave me output as. What is the prediction of the model? Okay. So take a test image I, okay, and then what is the prediction of that ith image? That is what is written over here. That's shown over here.
So
So first
is kind of a vectorization, sir.
It's just a visualization of what your network has done.
No, I'm
So if
telling
this is
that
the image,
in that test image, we are taking all the X
not
test
all,
images from 10 to 10 plus
20,
something. Right?
10 to 20 I have taken. So 10 images. Yes. I have taken 10 images. Now prediction is that run convolution network on these 10 images. Okay. So for each image, there is a prediction.
Yes.
Okay.
So that will also store like a list or something.
Yeah. So, okay. So, yeah, exactly. So, okay. So data type wise, I can explain. So test image is a image, okay, which is 784 size vector, which has to be reshaped. Like that's what it does. Reshape into 28 cross 28, and then in the gray scale, you print it. Okay. That's what this IMShow does. PLT.IMShow does. Take the test image I, reshape into 28 cross 28, use the color map gray and show it. Okay. Then you print model prediction. So what is model prediction for ith guy? The ith model prediction for ith guy is a vector, okay, of size 10. But I'm not interested in vector of size 10. I'm interested in which entry has the maximum value in that. What it is most likely. So that is what argmax does. What is the argument for the maximum? That means which entry is the maximum. Okay. So it could be 0th entry which has the maximum value, or the first entry which has the maximum value, or so on. Okay. So whichever entry has the maximum value, that's your prediction. So if here's the image and here's the prediction, that manually you and I can check, right, to see how good did it do. So that's just a kind of visual confirmation that how good my network is working. I mean, if the network, all this analysis gives you something, oh, it is 99 point correct, but how does 99% look like? It means that if I pass on like this, here I only pass 10 images, but suppose I pass 200 images. Okay. And on average, for 99% accurate, on average, I will have 2 of them wrong. Right. So right now here it is 97 point some percent. Let's just say 97.5% accuracy. That means if I throw 100 images, on average 2.5, maybe 3 images will be, prediction will be wrong. Okay. So manually we can check only if the large number of predictions are wrong. So it's one thing to see that my predictions are right. The wrong predictions teach you a better task. Okay, better thing. So then you know where to make corrections. If your model is giving not very good accuracy, then you just print where it's getting confused, what looks like what, why it is saying that this is 3, why it should say it is like 8, okay, or something like that. So then you can start looking, and then you can tweak your model, where to tweak and how many layers to add or subtract or something like that. Maybe in the first layer you want to increase the number of channels or something like that, or change the size of filter. So those things you will be able to make decision if you can print and visualize how good or bad it is doing on a given sample. So this is just a visualization of that. Any more questions?